Welcome to Lesson 30, Orbits and Satellites. We've got gravity, circular motion and potential. Now let's put them all together and launch something into orbit. Here's the plan for today. A satellite is just something in orbit. Although we usually think of satellites as metal boxes with solar panels, a natural satellite could also be something like the moon. Everything we've proved for planets applies equally here. Gravity supplies the centripetal force, and that gives us Kepler's third law. T squared is proportional to r cubed. And that relationship is genuinely useful because it means the orbit radius fixes the period. Choose your height and the period is decided for you. You don't get to choose it separately, which leads directly to something rather clever. Suppose we want a satellite that hangs permanently above one spot on the ground, so a TV dish can point at it and never move again. That's a geostationary satellite, and it has 3 defining features. Make sure that you learn all 3, because the exam can ask for them. 1. It stays above the same point on the Earth's surface. 2. It must orbit above the equator, and that is one that people forget. Think about why. The satellite's orbit has to be a circle centred on the Earth's centre. The only such circle that keeps pace with a fixed point on a rotating Earth is the one directly above the equator. Any tilted orbit would drift north and south over the ground. And 3. Its period must be exactly 24 hours, so it rotates in step with the Earth. And by Kepler's third law, that period fixes its radius, which is why every geostationary satellite in the world sits at the same altitude in one crowded ring. A related but slightly different word, geosynchronous. That just means synchronized with the Earth's rotation, a 24-hour period, but it need not sit above the equator, so it doesn't stay fixed over one spot. It comes back to the same place each day, but wanders in between. So every geostationary satellite is geosynchronous, but not the other way around. Geosynchronous satellites orbit at a slight angle to the equator, and from an observer on the Earth, the satellite appears to move up and down vertically. This makes sense when you think about it, as we've specified that it has to be moving horizontally at the same speed, but we didn't specify anything about it moving vertically, so it can move up and down. Now the energy. Start where we always do, gravity providing the centripetal force. So mv squared over r equals big G mm over r squared. Rearrange that to get v squared equals gm over r. Now substitute into the kinetic energy, a half mv squared, and you get the kinetic energy equals gmm over 2r, positive, as kinetic energy always is. The potential energy is m times the potential, which from last lesson is minus gmm over r, negative, as we established. Add them together to get the total energy, and you've got gmm over 2r minus gmm over r, and that comes out to minus gmm over 2r. The total energy of an orbiting satellite is negative, and those minus signs are correct. Don't be tempted to lose them. In fact, a negative total energy is exactly what tells you the satellite is bound. It doesn't have enough energy to escape to infinity, where the energy might be 0. Push its total energy up to 0 and it's gone. And that, in effect, is escape velocity all over again. That's the end of the video. Next time we switch from gravity to electricity, and you'll find that the maths looks remarkably familiar. Thanks for watching, and check out my tutoring page below.